Okay, so welcome back for the second half of the day. So the last two segments of today are composed of presentations by 4 researchers from across campus, followed by a panel conversation. The first of those presenters will be Dr. Aaron Wilson. He's both with the Byrd Polar and Climate Research Center and also with OSU Extension and the College of Food, Agricultural, and Environmental Sciences.
Well, good afternoon, everybody. It's certainly a good thing to be face-to-face, even in this hybrid situation. So that's actually the second event this week. Had the Extension A&R retreat over at the 4-H Center this week, and we were able to, I met about 30 new employees with Extension that I hadn't even seen yet in person. So that was pretty nice. We all set up?
Almost. Just gonna hide a few things, hopefully.
All right. Excellent. So yeah, welcome back from lunch. And so being the first speaker after lunch, I'm going to try to pull us all back together and kind of maybe float at the 30,000 foot level a little bit to talk about climate and to get us set up for this panel, perspectives on climate, water, and health, and focusing on the climate aspect. But a couple of the themes this morning, we had a great session this morning, didn't we? Talking about the human element and the human impact. And that's what I think this afternoon we want to do, is bring what we're learning and thinking about climate and bring it back down to that people level. All of us understand that it's the interactions at that personal level that are really important. So many of you know, is this working? This isn't working now. That's all right. We'll go this route or not. There we go. Weather is an awesome thing, is it not? Okay. Weather is absolutely fantastic. What you're looking at here is a model simulation combined with satellite observations of smoke, sea salt, and dust from the hurricane season of 2017. And I'm just going to be quiet for just a second. It's pretty amazing, right? Weather is in constant motion. It's absolutely critical to everything in life that we have here on Earth. This happens to be Hurricane Harvey. Coming into Texas to drop 65 inches of rain in Beaumont, Port Arthur in 4 days. Anyway, so we have all these fantastic features of weather, of temperature, wind speed, moisture, rapidly changing on these fast and short time scales and continuously evolving around us and moving. And so to watch the smoke and the sea salt and the dust just move around the globe, I find that really fantastic. And it's really the scale that we live in, right? We're experiencing weather with our senses. This is what we're seeing, but just given a couple of minutes of looking at this animation, you're probably already seeing patterns in the data. You're seeing certain motions in the data. And over a long period of time, these weather patterns are establishing the types of weather that we expect over the longer term period. Now, I've been here at Byrd Polar for, what are we going on, 13 years. Way back when, I saw Lonnie use this analogy one time. Probably I've used it 350 talks since then, which is the dog walker example here. So when we're zoomed in pretty close, it's hard to distinguish patterns. But as we pull out in this little animation, you're going to see the dog is walking with the dog owner. Now, what does this have to do with weather? Well, that dog is driven by some natural tendencies, right? If you're walking your dog, you know, fire hydrants, other dogs, a McDonald's wrapper or something, that dog could be moving in the opposite direction that you're moving, probably most of the time, actually. That dog doesn't want to follow along. But that's got some chaotic motion to that dog versus what you see that the dog walker or you're taking. Now, overall, we know statistically, we can define the path of the dog by the dog walker's path, those footsteps there. So even though we have those chaotic ups and downs, the variation in the dog's path, that mean path defined by the climate and where we expect to be in a couple of minutes is based on that climate, that dog walker or the climate path. So the dog walker being the climate, the dog being the weather. I have found this to be such an effective metaphor for explaining the relationships between these two variables and helping folks to understand what it is that we're trying to explain, okay? Now, this next animation is showing, and probably many of you or all of you have seen this change, talking about surface temperature anomalies. in 5-year increments from the late 1800s to 2020 here, just showing overall throughout the last 130, 140 years, we've had areas of cooler than average or warmer than average regions across the planet. So we get to about the 1970s, and then we start to see a really stark change in that tone, 70s, 80s, 90s, 2000s, and beyond. So we talk about this Arctic amplification or the warming across the north and uneven heating and most of the areas being warmer. And 2020 is actually the second warmest year on record for the globe back to 1880. It's only behind 2016 by 0.04 degrees Fahrenheit. And you can imagine that's probably within the error, right? So we're talking about the warmest year, nearly the warmest year on record. But what's even more amazing, and you can see that in the time series on the right here, looking at the historical perspectives, and you know, the top 10 warmest years have occurred, all occurred since 2005 for the globe. How many in here were born after the February of 1985? Anybody? You've never experienced a cooler than average month for the planet. Okay, 1985, the Reagan administration. That is a little bit sobering, right? It's a little bit sobering. And it speaks to a lot of the researchers and their work that's been going on for decades here at the center. So recently we had the new IPCC report, the AR6 report, and I wanted to pull out the key statements that were made in the climate change physical science basis here, and a lot of words to carry with us today. The first one is unequivocal, right? It's unequivocal that humans have influenced, have warmed the atmosphere, the ocean and land, and set into motion the changes and the feedbacks that we're seeing today. Another one is scale, the scale of the recent changes. You heard about the acceleration of glacier loss today in Lonnie's talk and Brian's talk. Unprecedented over many centuries to many thousands of years. Researchers in here provide the foundation for that distant look back to understand that this has not happened. It's unprecedented, right? And then it's already happening. So my background is I get to work a lot with the farmers across the state of Ohio, talking about climate change. And they're going to tell you, we're not going to talk about climate change a lot, perhaps, but things are happening, right? Changes are happening. They're experiencing those changes. And it's a very good place to start. And of course, evidence of observed changes in extremes. We hear a lot about those extremes. And I'm going to talk about those just a little bit and hopefully play into the following 3 talks that we have here today. So very simple physical basis for this. We increase our greenhouse gases, our CO2, our water vapor, evaporation increasing, and warmer oceans leading to more water vapor in the atmosphere. That absorbs more of that outgoing infrared energy from the Earth's surfaces. Our temperatures warm up and we get a lot of positive feedbacks, loss of sea ice, more water vapor in the air that then contribute back to that warming. But we're here to also today to talk a lot about water, and it's very much tied to our water cycle, right? Very much tied both from land warming and ocean warming, evaporation, more water vapor into the atmosphere, providing those warmer conditions, but also the opportunity for fronts to come in and squeeze that atmospheric moisture out. We're going to talk about some of the extremes that we've seen recently, but there's certainly a lot of research that's ongoing to tie this back physically. And this is a nice paper out of the National Academy of Sciences, the proceedings back in 2018. And they were trying to think about some simple analytic framework to think about and tie in some of the correlations or the relationships that we see between ocean warming in blue lines on this time series and land warming, okay? So both temperature and humidity trends over land and the oceans between 1979 and 2016 over land are linked to these warming oceans, right? We know it's more than just the land heating up, but also the water. And after all, we're a water world, right? So climate is very much tied to that water. And so they're simple models really based on some atmospheric dynamics and moisture transport. We're not here to talk dynamics today, but certainly it helps account for the equal changes that we're seeing in the specific humidity or that measure of the absolute water vapor, both over land and ocean. The bottom graph's looking at relative humidity. And you know, what's interesting as a weatherman, what do we often report? Relative humidity. Farmers are really tied to relative humidity. And in fact, we've seen a decrease in relative humidity over the last several years. Why? Right? There are a lot of reasons. There's some reasons a lot of uncertainty associated with that, but one of them, right, very much tied to temperature. Temperature is increasing, outpacing water vapor, things like that. Still some things to learn. I mentioned we're a water world, and Lonnie was talking this morning about the sites and all the tropical glaciers that are studied in the human population. Well, monsoon rainfall impacts more than 2/3 of the global population, right? Our major monsoonal systems across the earth. This is a recent review article, just really recent here this year from BAMS, the Bulletin of American Meteorological Society, looking at a review of these monsoon systems and the impacts of climate change. So obviously attributed to warming and urbanization over the past century, already causing a significant rise in extremes, and I'll get to those in a moment. But the trends in the monsoons do vary by region. There's a lot of variability depending on the monsoonal seasons that you see. So kind of that turquoise, I would call it turquoise, or a lot of those are the Northern Hemisphere summer monsoons. The beige or brown are the Southern Hemisphere summer monsoons. But there's some variability between these monsoonal systems where we might see a little bit of decline in South Asia and North America, but increases in Australia, Africa, South America as well, with considerable variability associated now. We're tying these two things like aerosols and ozone depletion and circulation changes, right? So very important that, again, this water cycle that climate is so intricately tied to is impacting all of us. And in these major monsoonal regions, it's impacting, again, 2/3 of the global population. This is pretty important, right? When we zoom into the United States and not just thinking about precip, but we're also thinking about temperatures, we know that our more than 95% of the US land has demonstrated an increase in annual average temperature. My farmers are interested in more than just annual averages. And what are they experiencing? They're experiencing rapid changes and increases in spring temperature, fall temperature, as well as wintertime temperature, but less so during the summer. This past July here across the Midwest was a good example of what's been more of the trend, which are daytime highs a little bit cooler, nighttime lows quite a bit warmer due to more water vapor in the atmosphere. And we had a lot of wildfire smoke in the air this July as well, which cut down on solar radiation, and that had an impact. So we see a lot of the seasonal changes that are having an impact as well. These are both from the last National Climate Assessment. The next round is due out late 2023. With precip, we're looking at a 4% increase in annual precipitation, but not everywhere. There was a student talk, I can't remember her name, Kay, did she go by Kay, right? We talked about the droughts and showed pictures of the Southwest, and then talking about drought here in Columbus. I thought it was interesting when she was looking at rainfall for summer and a general increase. We've actually seen June precip increase, but July and August, specific months, that are flat to negative around the state. Big increases in spring rainfall, fall rainfall. And for a farmer, for instance, when I'm talking to them out and talking about what their perfect season is, they want a wet spring, a dry growing season, and a wet fall. No, they don't, actually, right? That's exactly what they don't want to see. They need that rainfall during the growing season with time to plant and harvest. So the trends that we're seeing here, even locally, are impactful. Back to this idea of extremes, and I want to stay here for a couple of minutes. Looking at every way that we break down different statistical measures of our extreme heavy precipitation, for instance, just one type of extreme, we're increasing, especially across the Midwest and the Northeast. We got some updates to the state data that's coming in relatively soon, hopefully by the winter. But the last round, looking through 2014 here in Ohio, basically since the mid-90s, we've seen a steady increase, or I should say a stepwise increase in the number of extreme precipitation events. And if you look back into the historical record, there are 3 years that are in those other peaks, 1913, 37, and 59. Now I use this to say, obviously, 13, 37, and 59 were major flood years in Ohio. So the idea here, we're wet and getting wetter, is that even in drought, right? We could talk about that. Even in drought, the opportunities for flooding from intense rainfall are ever present, right? We see that. And earlier I'd asked the question about, we're also seeing, and I'm not showing you here today, is how rapid we're switching between extremes in the hydrologic state. from very wet to very dry. We've got some colleagues across the Midwest that are looking at that as well. Billion-dollar weather and climate-related disasters in 2020 numbered 22 since 1980. That was by and far the greatest amount that you see there. But they vary in terms of their characteristic across the country, across the landscape. You go out west, it's the heat waves, it's the wildfires, right? That's really characteristic of what's happening out west. A number of landfalling hurricanes and tropical systems last year. If I believe it, we had 8 last year and 8 this year so far in terms of landfalling, although the devastation was a little bit worse last year. Anyway, so a number of these billion-dollar weather disasters. Here in the east or in the water-rich region, it's often through that water interface. You look at the amount of damage that's been done in Ohio from weather-related disasters, over 200 million between 2008 and 2017 on water. Saw a report yesterday morning that on average, the US is experiencing a $1 billion weather disaster every 18 days. Every 18 days, we're experiencing a $1 billion weather or climate-related disaster. But are we recognizing it? Are we feeling it? This is a new Marist poll here from NPR, looking at the question, in the past 2 years, have you ever personally been impacted by an extreme event where you live? 71% reported no, they hadn't. And that's the character of these extreme events. They're highly localized. And our action that depends on what's been demonstrated, our action depends on whether or not we've been impacted or feel impacted. That's very important. You don't have to ask folks in Central Tennessee, right? 17 inches of rain this summer, and this is going to be cherry picking some events, right? Reynoldsburg, 4.5 inches of rain in an hour and a half back in July of this year, right? Smoke in the valley increases doctor visits. Just a picture of the wildfire smoke. Anybody hear about the Italy event on Monday from Roscaglione, right? 29.6 inches of rain in 12 hours, okay? A city near there picked up 19 and just over 6, and a city, I think a little bit west and south, 7.1 in an hour. Now, atmospheric dynamicists out there are thinking, man, that the energy, the amount of what we call moist static energy or the amount of water vapor that's in the atmosphere to bring about that change is really extreme, right? So we have to face it, right? We have to face our idea about extremes, and we have to do so even when most of us are reporting we haven't been personally impacted or felt that event. So as we switch into the future and to kind of set up, the things that we're thinking about and the impacts, we've advanced now in our latest modeling scenarios. Scenario is, I think, maybe it's half science, half art for those that have been involved in trying to understand scenarios. Why is that? Weather is difficult to predict. Predicting human behavior is even more difficult, right? But we have choices to make, and we look at the future projections under these different scenarios, and I think the right-hand side shows it the clearest. Are we going to stay below 2 degrees C, right? And what is it going to take? And more importantly, depending on that scenario, that path that we choose, right? We get to choose that path collectively. There's even more severe consequences that come from those warmer temperatures out into the future. And if we look at a snapshot, just looking at simulated changes at a 1.5 degrees, 2 degrees, and 4 degrees C, there's no question that even though we're just increasing 0.5 degree C and 2 degrees C here in terms of temperature across the globe and the changes, the impacts to humans is exponential, right? The differences between 1.5 degrees, and our reports are showing that, versus 2 or even 4 degrees C warming by the end of the 20th century here, relative to 1850 to 1900, those are big changes, not just in temperature, but also in precipitation, right? So when we think back to those monsoonal systems and we think about the folks that are living in South or East Asia, and whether or not we get more frequent or less frequent monsoonal collapse, right? We think about the Amazon. We think about, in all 3 scenarios, the decrease in that amount of moisture precipitation over the Amazon. What happens? That's the water driver, right, of our Earth. almost a heat engine. So again, it's about changes associated with behavior. And I don't expect you to read all of these, but I certainly encourage you to go look at the shared socioeconomic scenarios, both for IPCC and also ultimately for National Climate Assessment as we get into those. But are we likely to take a sustainability road? Low challenges to both mitigation and adaptation. I like how these are framed. Or are we thinking more about this rocky road in the middle, high challenges to both? A lot of resurgent nationalism, concerns about competitiveness and security, or fossil fuel where we might be able to adapt quite a bit due to technology, but maybe mitigation and getting to cleaner energy may not be as rapid as we need. Ultimately, we've got a lot of impacts that are going to continue to happen. And that's where I really want to set up the rest of these talks today. And I like how the Met Office uses this example. You've got your drivers of climate change, right? The greenhouse gases, land use changes. There at the middle. Changes to our climate system that I talked about today, more extreme weather, warmer temperatures, rising sea levels that we've talked about today, decreasing ice that we've talked about today. But look at all those impacts on that outer circle. It impacts and it connects to everything we do as humans here on Earth, from our health to our water and all the social aspects, all of the interactions and the interpersonal actions that we have to think about, our food security system, our food, our farmers, our water quality, water quantity, the list goes on, right? The list goes on. So it gives me kind of, obviously an honor to talk about these things today. And really, I enjoy the opportunity here at the university and beyond to work in that interdisciplinary space, because it's much more than just climate scientists right now that are going to take to solve these issues. We all have to come together. So I appreciate the time, and we'll talk in a little bit.
So we'll switch over to the next slide deck. We won't take questions at this point. Kind of jot all your questions down because those will be for the panel conversation afterwards. If you are online and you want to use the Q&A button, you can go ahead and post those questions at any time. And in fact, we would be going into our break. It would be helpful to see all those questions already there. So feel free, don't hold back. Go ahead and post them now. So we'll transition out of the next speaker. Rachel Coyte is with the Global Water Institute. I think just arrived on campus recently.
Yes.
So welcome to Ohio State and welcome to Columbus.
Thank you.
Give us 1 second to do the slide deck.
No worries.
All right.
We good?
Almost.
Almost.
Just want to hide this little toolbar. Have you used presenter tools before?
Just gonna move forward, right?
This you can forward it back. Pointer. There's the pointer on the mouse.
Great. Okay. Thank you. Hi, everyone. Good afternoon. I am Rachel Coyte. As mentioned, I am with the School of Earth Sciences as well as the Global Water Institute. And I'm really thrilled to be with you all as a new member of the Ohio State community. I'm an environmental geochemist. And if you kind of break that down, that means that I operate in the space that overlaps between geology, environmental science, chemistry, maybe a little bit of biology here and there. And I mostly am looking at things that are happening at the Earth's surface or just below the Earth's surface. Now, this encompasses a wide range of different topics. Environmental geochemistry is incredibly broad and a really great field that I encourage you all especially if there are any students in the audience to look more into. It could be anything from looking at the global cycling of phosphorus to looking at health effects of artisanal gold mining in Peru. But for me personally, my research has mostly focused on a few different topics. The first being water quality, and in particular, inorganic water quality. So I look at things like fluoride, arsenic, uranium, a lot of times in groundwater, because groundwater is incredibly important. 98% of Earth's freshwater resources are in groundwater. So we should all appreciate groundwater more. And these elements, these inorganic contaminants that I study, they can be from human sources, things like agriculture or industry. They can also be from the Earth itself. So a lot of contaminants that we think of as undesirable in our water resources, especially things like arsenic, can actually be naturally occurring, which I think a lot of people don't necessarily think about unless they're directly exposed to them. Obviously, since this is science, lines between anthropogenic and non-anthropogenic or geogenic can be a bit blurry. For example, I study a site in India where we have high uranium in the groundwater. The uranium is geogenic, meaning it comes from the Earth, but agricultural effects have made the problem significantly worse. The other area that I have focused on in my research, and which overlaps in many ways with this water quality area, is energy in the environment. So I have focused mostly on fossil fuels, looking a little bit at fracking and fracking flowback water quality, but a lot of my work has actually focused on coal combustion residuals, so coal ash, and what the fate of coal ash is in the environment. And so this background really informs what I'm thinking about when I think about climate change and the future of environmental quality. And so with that, I'm going to give a little bit of an aperitivo for a few topics related to climate change and environmental quality that hopefully can serve as a nice little taster for our talk later on with a panel. The first topic that I want to discuss is salinity and salinization. I'm going to be talking mostly about this with regards to water resources, though soil resources are deeply connected with everything that I am going to be talking about today. And a lot of the salinity things that I am speaking about with regards to water are definitely applicable in a soil setting as well. Salinity and salinization is really a much beloved topic by a lot of environmental geochemists because of its got a myriad number of causes and potential causes and contributing factors, but it also is an incredibly important topic. And if not managed correctly, salinization of water resources can be really devastating to communities which it affects. I'm going to start with talking about some of the climate drivers of salinization. Climate drivers are really important, so much so that we actually usually call climate drivers primary salinity when we're talking about salinization of water resources. And one of the chief ones here is aridity. So being in a location that has high evapotranspiration and low rainfall or low recharge. This causes the buildup of salts and over time, the salinization of resources. This usually takes quite a long time. This is not something that's going to happen overnight. And there are many parts of the world today that have experienced this type of salinization through natural variations. If you've ever been to the Salt Lakes of Australia or the Great Salt Lake in Utah, you've experienced an area that has seen this type of salinization naturally. This also happens in groundwater and other types of water resources. Let's see. Just because an area is arid or has experienced some types of salinization doesn't mean that it's immune from climate change effects and perturbations to the system. So variations in rainfall that require more abstraction of groundwater, for example, can really cause disruptions to the system for people that are living in arid and semi-arid areas. A good example of this are cases where you have an aquifer that is fresh on top and saline underneath. This happens in many parts of the arid world, particularly in the Middle East, where you have fossil groundwater that is fresh, underlined by more fossil groundwater that is saline. And when you start pumping too much of that fresh groundwater, it actually becomes contaminated by the underlying saline groundwater, which can be really devastating to people that are relying on that water source. When we're talking about climate change and areas becoming more arid, so not areas that are already arid and semi-arid, but areas which might be experiencing for the first time a period of primary salinization, because this takes longer scales, actually a lot of what we're worried about from salinization effects is coming from that secondary salinization that can be caused by human pollution, for example. So agricultural runoff, different types of industrial pollution, et cetera. Because when water levels start to drop, that makes resources a lot more vulnerable to secondary salinization as well. So these things go hand in hand as climate change occurs. And the last topic I want to talk about when we come to salinity is that you don't have to be in an arid environment or an environment that is becoming arid to experience problems with salinity. And one of the most important things here is saltwater intrusion. So coastal communities are especially vulnerable. Saltwater intrusion is one of the most widespread and important processes that degrade water quality, because something like 40% of all people live within 100 kilometers of a coastline and are reliant on coastal aquifers for their drinking water. This figure, which is from a really beautiful review of the topic by Tully et al., actually called The Invisible Flood, I highly recommend to anyone who is interested in this particular topic. So when we're talking from a coastal perspective, some of the climate drivers of salinization are listed here. So sea level rise, droughts, as well as storms and tides. So as we have these climate factors that can increase the problems of coastal salinity of our coastal aquifers, as well as coastal surface water resources, we also have to take into account a lot of human aspects as well, including water table use. So particularly as populations grow along coasts and droughts become more of a factor to reckon with, we may see higher withdrawals, which just make the problem worse through withdrawals in our aquifer, or diverting coastal water resources more inland. The next topic that I want to talk about are rainfall extremes. And I'm going to start with what a lot of us think of when we think of rainfall extremes, which is flooding. Flooding happens, and we're all familiar with the physical aspects of flooding, the tremendous loss of human life that can happen, the property damage that can really devastate communities, but it can also come with a water quality cost. When flood waters come through an area, they pick up everything that is around its environment. And depending on what environment that is, that could mean human and animal waste, that could mean industrial pollution, pesticides, or perhaps coal ash. I'm from North Carolina, and this is a photo from the North Carolina, not even really the coastal area, but where several hundred miles inland, where we have stored a great deal of coal ash in ponds that cover the coal ash in just an open reservoir, essentially. Think of an impoundment. When the floods came through, after this was Hurricane Florence, I believe, 3 or 4 years ago, at this point, it pulled out massive amounts of coal ash from these impoundments and spread it all over the environment. There were some really sad photos from the news of turtles covered in coal ash, but even more scary in some ways is it's people's backyards as well. So oftentimes when we're thinking about groundwater, we have this perception that groundwater is more protected than surface water sources from pollution coming from the surface, which can be true in some ways. But during a flood, we have an extra added danger of something called direct ingress, where water is directly introduced to a well during a flood event, which can more easily transport contaminants into the groundwater. And additionally, depending on the aquifer, not all contaminants may be filtered out through that infiltration process to begin with. So it's something we need to worry more about. The amount of studies that have been done on this are mostly focused on pathogens, and it has been shown that certain pathogens certain waterborne pathogen increases can happen after floods. But these studies are mostly done in municipal wells, which have higher levels of protections against, they have filtration measures, they have monitoring measures, And there really hasn't been a lot of work done on private wells. The other area where I'd like to see a lot more work on this done is on things other than pathogens, things like pesticides, things like coal ash, depending on where the locale is. There are different types of contaminants that we might be worried about from a water perspective. So you don't have to have a massive flooding event for there to be water quality concerns related to extreme precipitation events. And I was actually really glad that one of the students this morning gave a lovely talk about this right here. Who knows what this is? Yes, harmful algal bloom, right in our backyard here from 2014 Toledo, when they had that big harmful algal bloom that shut down water for a while. And this event really raised a lot of awareness about this issue. From a water quality perspective and a precipitation changes perspective, a lot of research is pointing now towards earlier precipitation and heavier precipitation, so perhaps precipitation that may have been snowfall in the days of yore, coming through and delivering a lot of phosphorus early into the year into water resources, being something that can trigger some of these more harmful algal blooms. So this is just one example of ways in which precipitation pattern changes can make a big difference in water quality. And the last topic that I want to talk about today is a little bit different from the others that I've talked about. This one is less related to ways in which climate change is going to affect environmental quality and more related to ways in which our decisions about how we approach climate change will affect environmental quality. And that's resource extraction. Something that I don't think gets talked about enough is how our mineral needs are going to change significantly if we are to achieve our climate goals. These figures from the IEA, they wrote a wonderful report about this topic that I highly recommend to anyone who's interested. These figures from the IEA show on the left, minerals that are used in electric cars compared to conventional cars. And then on the right, minerals used in clean energy tech compared to power generations, other types of power generation sources. So electric cars, as you can see, require way more of almost every single type of mineral resource than a conventional car. And if we're going to reach the goals that many countries like the EU have set for replacing our entire fleet of conventional cars with electric cars, we really need to make sure that we have the mineral resources to do this. This is even more striking when we look at the clean energy technologies. The amount of, say, silicon that's required for solar PV, or the amount of copper that's needed for offshore and onshore wind, we need to really be ramping up our production of these materials. However, that comes with a significant cost. And actually, this was quite timely. This morning, I woke up and I saw an article in the news talking about how there's a big conflict in Spain right now between farmers and individuals who want to, or in companies that are trying to start rare earth mining in certain regions in Spain. And the conflict is because, one, Spain has the second largest stores of rare earth element ores, I guess, in Europe after Finland. And so a lot of people clearly would like to be producing that domestically, benefiting from that resource extraction and also not relying on other countries like China for these resources. But the farmers are worried about environmental degradation, and quite rightfully. Mining comes at a cost, and we can do our best to try and perform it sustainably and to try and be responsible. But it is there are environmental costs to all types of mining. And we need to recognize that and have open conversations about this. Currently, there are our production of lithium. As you can see up here, this is the water costs. So the requirement of water use for certain productions of minerals. Lithium is one of the highest water intensive minerals to mine. The largest stores on Earth of these elements are both in arid areas in Australia and Argentina. Same thing with the waste products. So after we've done the mining itself, we're still going to end up with massive waste products. It's the same problem that we have with, our current fossil fuel resources like coal. We end up with massive waste products that we need to come up with plans for dealing with if we are to reach our climate goals. So I'm going to go ahead and stop right there. And I look forward to chatting with you all during the panel discussion. Thank you.
Hey, remember, if you are in the remote feed, feel free to go ahead and put your questions in the Q&A now so we can have those all already available before we start the panel. So we'll bring up the next slide deck. Our next speaker is Michael Bisesi. He's with the College of Public Health at Ohio State.
Yeah. If you want to continue.
Yes, please. Thank you very much. Well, good afternoon, everyone. So it's self-explanatory what I'm going to focus on. However, I'm going to look at this from a little broader perspective. And also when I say perspective is, there's all these forecasts out there from different agencies, different organizations, and clearly we need to pay attention to them. But the magnitude of impact to human health and other living organisms is really mostly unknown. And much of the projections focuses, when they want to have a quantitative projection like this one, focuses on mortality. How many deaths, how many additional deaths as a result of climate change? Well, the reality is there'll be an even higher number of individuals who become ill as a result of climate change than a number that actually die. So the reality is these are projections. I don't pay a lot of attention to the quantitative aspects. More of my focus is on the qualitative aspects. And to me, there are clearly enough data, even in what's being experienced presently. From the first two speakers, you can see that there are measurable changes. So we do need to pay increased attention to some of the impacts. So my background is I'm an environmental and occupational health scientist. That's a subspecialization of environmental science. I had outstanding mentors when I was a student, and I morphed into a generalist by design. And so I tend to look at the connectiveness rather than focusing on one matrix or one disease. And so today I'm going to insert a little bit, only a little, because I'd be somewhat hypocritical not to, in addition to the human health, the broader One Health paradigm a little bit, and that'll become evident in a moment, from the environmental public health perspective. And so my slides are a little busy, and that's also by intent, because I just wanted to use them more as triggers just to make some points. So when we say the environmental health science or the environmental public health perspective, which they mean the same thing, it goes beyond identifying a matrix of air, water, soil, or food, or even building materials, and answering the question, is that matrix or environmental medium contaminated? And if so, contaminated with what and at what levels and so forth. But it extends further to identifying what are the pathways that a hazardous agent, such as an infectious microorganism or a toxic chemical, can now become transported from some source through some media and actually come in contact with a living organism. Most of my focus throughout my career has been on humans, but over the last decade as co-founder of the Global One Health Initiative with Dr. Wanderson Gabreas, we've expanded the principles beyond humans. And so that's what this diagram here is that when we talk about exposure, and this is something that oftentimes you see, is that someone will do a study on a surface water, say these contaminants were found, and then look up the contaminants and say these contaminants cause this type of disease. And that gets into the dispatch or some other media for it, and it can initiate a lot of distress among the general public. And public health approach, and environmental public health in particular, is we don't want to add to a problem. In fact, we don't want to claim there's a problem without data, right? So all we would know is that that surface body of water is contaminated with some hazardous substance. But from that, the question is, if exposure occurs, right, from some source, and that's what this environmental health model that a colleague and I developed about 20 years ago, you say, what are the pathways for exposure? What are the media that would be involved, or is it a single medium? And then how is it distributed and how does exposure occur? But even if exposure occurs, we define that as external exposure. Even with exposure, you don't assume disease. And even though today's not focused on SARS coronavirus 2, you've been deluged with information over the last 18 months about this and beyond. And not all contaminating settings result in exposure, not all exposure results in infection, and so forth. And I'll talk about that continuum in a moment relative to applicability to climate change. And so where I'm slipping into One Health approach is we know that climate change is having direct and indirect effects on the environment. Let's start there. You just heard many of them. And when I look at the environment, I always include at least 3 major media: the air, water, and soil. And then the 4th one would be food. None of them are independent from one another. So if we say the air is contaminated, you have to question, are the surface bodies of water also being affected by the air quality? And what about soil and so forth? And so we look at this from a more holistic approach. And if we have a source of exposure, the question is, if there are other living organisms in addition to humans, is there concurrent exposure to multiple levels of life, micro, meso, and macroorganisms? So some foundational principles before I go into some key examples that'll build off of what you've already heard today. So just some foundational principles. And what I want to focus on is that we know that from a human contribution, the anthropogenic contribution is been use of fossil fuels, right? And one could add the qualifier excessive use of fossil fuels, but everything is relative. But if the fossil fuels were just carbon, hydrogen, and oxygen, and combustion of those materials from power plants, manufacturing industries, and transportation sources, which are the 3 major consumers of fossil fuels, not the only, but 3 major ones. If there was 100% combustion efficiency, you'd have no smoke, which means you'd have no particulate matter. You'd have no oxides of nitrogen because there'd be no nitrogen in the substrate. So theoretically, you'd only have carbon dioxide and water. Now that would still be an issue because we know that carbon dioxide among the major greenhouse gases represents about 70%, 75% of the greenhouse gases. So that would be a concern relative to the greenhouse effect that Aaron was talking about. But the reality is we still get a lot of CO2 because it's rare to have 100% combustion efficiency, even if you were to try to design the most optimal incinerator, right? There's no automobile engine, there's no furnace that has 100% combustion efficiency. So here's what we know. We have inefficient combustion. We also have other elements, right? Think schnapps, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, plus the metals, right, that can be present, like in coal, in other sources from the geochemistry. And so those elements are part of the combustion reaction. So instead of an efficient combustion, we actually have inefficient combustion. And so from a greenhouse perspective, CO2 gas is still an issue of concern, but simultaneously, we're getting the release of airborne particulate matter that you hear of as smoke. Smoke is a solid, it's particulate matter, and within it, you have metals, but you also have numerous types of cancer-causing polyaromatic hydrocarbons, as well as polynuclear aromatic hydrocarbons, and oxides of nitrogen, which contributes to that, oxides of sulfur, and so forth. So we really have a more complex issue than just management of CO2. We have the broader issue of other contaminants simultaneously. In addition, the release of those from the major sources in their parent form may not be the same, and once you have the photochemistry effects involved. And so the reality of it is, as these primary air contaminants, including CO2, are being released into the environment, our concern with CO2 is not as a toxic chemical. Carbon dioxide is relatively non-toxic. It's a simple asphyxiant. It's more of a concern if it's purging oxygen out of a confined area. But as a molecule, CO2 itself does not trigger some type of illness. But all the others, the oxides of nitrogen, the volatile organic compounds, which result from other uses of carbon-based substances such as solvents, but also the fuels themselves generate volatile organic compounds. And you have a cascade of events leading to formation of ozone from the photochemical transformation of nitrogen dioxide, for example, into nitric oxide in a free radical, combining with molecular oxygen to give you ozone. And so this is thermospheric ozone, which is highly irritating, associated with respiratory distress, but more so associated with exacerbating individuals who have pre-existing respiratory illnesses, such as asthma, emphysema, cystic fibrosis, and beyond. And then photochemistry involves the combination of chemistry involving ozone and oxides of nitrogen and organic molecules to form photochemical smog, known as peroxyacetyl nitrate, or PAN. And this is an example of a secondary contaminant. So the complexity of it all goes beyond simply what's happening in contribution to the greenhouse effect, but simultaneously agents that are being released that we already know can have adverse impacts to humans and other organisms. And as was alluded to, that what goes up can come down. So again, acid precipitation is a great example where we know where air quality clearly can influence the quality of surface body of waters, as well as soil and so forth. So when we talk about, or at least the paradigm I like to talk about, is the direct impacts to the environment. And then from those impacts, are there direct impacts to human health or not? And the reality of it is that climate change involves a cascading effect where there's initial changes, and because of those changes, they contribute to additional changes. And therefore, predicting the effects associated solely with climate change is nothing more than that. It's a prediction. So I'm not devaluing that. I'm just saying it's not an absolute. And so trying to quantify it would make it very, very difficult. So I'm going to share just a few examples, but we're looking at direct, but mostly indirect effects to human health. So I just want to spend a moment before the examples and again, talk about the disease continuum and the principle of direct versus indirect. So the disease continuum is that just because there's a source of contamination, there has to be exposure before you can even talk about risk of disease. So the work that we do is more about exposure assessment, which is the exposure hazard assessment. And then with those data, you can determine disease risk. And so there must be a source. That's one of the foundational principles. What is that source? And is there direct or indirect exposure? Without that, then we don't need to talk about probability of disease. There has to be, so we have to start first by asking the question, is there an exposure hazard? And then we have to accept that if exposure always precedes disease risk, not all exposures result in increased disease, morbidity, or increased deaths, mortality. So it really is a continuum. And so this is the typical paradigm that I use to organize this in my brain. And that is direct exposure would mean we have a contaminated environmental medium and a human comes into direct contact with that medium. They inhale the contaminated air, they ingest the contaminated water, and so forth. Or it could be a non-human animal, or it could be a plant, again, slipping in the One Health paradigm. The One Health paradigm looks at the interface between human health, animal health. We have added to the paradigm plant health and environmental health. So it's that interface between and among. The indirect exposure means that there's an initial exposure to some life form. This example, I'm using a plant. So that would have that direct contact with some contaminated medium. That's directly exposed. It becomes contaminated. It may have adverse effects or not. But if now some other life form interacts with that contaminated, right? You're thinking of the food chain, then now this is indirectly exposed to the contaminated medium. And so that's the concept that you're all familiar with, the food chain, and concept of bioaccumulation, biomagnification up the food chain. So we are always trying to answer the question, is it a direct effect? For example, an herbicide applied to crops to control weeds, and we're consuming that without washing it. There's residue, and over time, there's enough residue and exposure where it has the potential, emphasis of potential, to initiate an adverse effect. That would be direct exposure. And then the indirect exposure, where we're drawing fish out of a contaminated source of water. Some work we did in Toledo before I moved down here. And the contaminated fish now becomes part of the food chain. The fish is directly exposed. The human is indirectly exposed by consuming the fish. So direct and indirect exposure. So looking at this from the climate change perspective, what did you hear so far today? What did you already know coming in? That most of the climate change has to do with temperature extremes and precipitation extremes. Not all. It's not only global warming, but that's certainly a big part of it. So we know that there are sources that are contributing to elevated temperatures, changes in extended seasons, precipitation, and so forth. So I'm just using this as an example. And if there's direct exposure to those factors, then we'd ask the question, what are those substances we're concerned about? And we'd also ask, are there other intermediate changes that have to first occur before we're concerned about exposure? And so in this general model, we know that already there are changes in ecosystems. So vectors, which by definition are living organisms that become contaminated, and they can move that contamination, such as an infectious agent, from a source to a receptor. And it could be a human, animal, or plant-based receptor. And so there clearly are signs and symptoms of changes that have already started to occur. There are projections that these will become magnified further, in that there'll be increased insects such as mosquitoes and arachnids such as ticks, just to name two major vectors that are going to be more common, right? So infestation of various geographic areas, the potential for spread to broader geographic areas, and increased probability of coming in contact if they're not controlled. And so by altering ecosystems, knowing that there can be changes to insects and arachnids and vectors, as well as overall infectious microorganisms, either the emergence of new strains of organisms, SARS coronavirus 2, or reemergence of organisms that we thought might have been under control. So there's a lot of pieces here. So just some general examples. As far as direct effects go, and I'm going to conclude with just focus on humans. As far as direct effects go, and I'm not talking about drowning in a flood, I'm talking about direct effects where there's cause and effect of some type of an agent, infectious agent or a toxic chemical, or a physical agent such as just the thermal contribution. We know that the high ambient temperature, as well as factors of the type of heat loads, radiant heat and so forth, it's not enough to just measure the temperature relative to the potential impacts to humans, but also look at it in the broader sense of heat index, which takes into consideration not only temperature, but humidity, and or wet bulb globe temperature, which uses a device like this. They come in various sizes, where we're measuring radiant heat, wet bulb temperature, where the thermometer is actually moistened, so that you can take into account high humidity, makes it more difficult for the thermometer to dry and cool faster, versus a dry bulb temperature. So this is an extension beyond a device such as a sling psychrometer that some of you or most of you may be familiar. But instead of looking at what is the overall wet bulb globe temperature and comparing it to guidelines, right? In the red, meaning when wet bulb globe temperature reaches a certain point, that would mean that the risk of adverse impact is increasing, right? And heat index, a very similar model, but looking at that interface using psychrometric charts with humidity and temperature. And we know that the extremes in the form of heat waves or just persistent elevated temperatures and a lack of cooling at night, especially in an area where there's a lot of blacktop and concrete, right? The albedo, where more heat is being absorbed than not, it creates elevated core temperatures. And depending on, is it people who are sedentary or people who are active, their risk of developing heat-related illness or heat-related death whether it's from an elevated core temperature or some cardiovascular event, such as a heart attack, is very real. And so this is part of the concern as a direct effect. And then briefly, moving into indirect effects, we know about the flooding and alluded to, as was mentioned, with flooding comes the potential for distribution, right? It's very disruptive. Distribution of sewage, whether it's land applied from agricultural settings, disrupting municipal wastewater treatment facilities, or combined sanitary sewers overflowing, but also toxic chemicals from various industrial sources and so on. And so indirectly, the post-flood events can leave behind dispersed contaminants that weren't there pre-flooding, thus doing what? Increasing the potential hazard, right? The exposure hazard. And where there's an increased exposure hazard, there's then the concern, is there increased toxicity or infectivity, which can lead to non-infectious and or infectious disease. But you can see that's indirect. A lot has to happen in between. Drought, which was talked about as well. Drought has influenced the ecosystem, so it leaves behind in droughts associated with elevated water temperature. Well, before you even reach this extreme of drought, just knowing water temperature, we know that water temperature as it becomes warmer favors certain types of pathogens, such as the Vibrio bacteria. Vibrio parahemolyticus is one of the most common infectious agents associated with foodborne illness from seafood, among others. In other areas where cholera is an issue, so where I do my work in Ethiopia and Kenya and Tanzania, cholera is a very big issue. So it all geography comes into play. And so there are a variety of factors that we need to consider, but also as the volume of water recedes, if the chemicals aren't volatile, such as the metals and some of the more persistent organic compounds, they become more concentrated. So now you've taken an already, I don't want to say bad situation, but a contaminated situation, and you made the magnitude of that contamination higher. And then wildfires, they're happening much more frequently. So I go back and forth between LA. My wife lives in LA, I live in Columbus. And the wildfires this summer, you knew it. You could see it, you could smell it. And so it's very real, but geography comes into play. But as Aaron showed, smoke doesn't stay within the boundaries of California. It migrates elsewhere around the world. And where there's smoke, we're concerned about inhalational exposures. So the indirect effect would be first the wildfires being more likely to occur because of lack of precipitation and increased dryness. And therefore, when the fire occurs, there's increased exposure to polyaromatic hydrocarbons, which are the primary concern with wildfires. And then to conclude, extended summer. As a result, we're seeing now that if the summer months extend, whether that's good or not from growing crops, I don't know that. Aaron probably knows that because some of which there is, and not everything's a negative to perhaps come out of climate change, or maybe some positives, but here's what we do know, that ticks are changing, right? So even the variety of species of ticks is increasing right here in Ohio and beyond. So extended summer can influence certain pathogens. It's clearly influencing the amount of allergens being released into the air. So variations in pollen and variations of how long these pollens are being dispersed into the air. So you can't guarantee, oh, in May, my allergies are the worst. Well, maybe May, June, July, right? It's spreading out a little bit. And so there are factors to consider, as well as increased exposure to outdoors and therefore sunlight, and there may be increased risk of developing dermal or skin cancers. So there's any number, and I compartmentalize this into a very short presentation, but it's very complex. But what is known with certainty is most of the impacts when we talk about human health from the public health impact perspective are indirect. There's something happening in between. So I'll conclude that.
Reminder for anybody who's on the Zoom call right now, we have about 60 people there. Just continue to add questions to the Q&A button. The next presenter will be Smitha from the College of Social Work. She's also a new faculty member who just joined us this semester, and we were fortunate enough to connect, I think, in your first few weeks on campus.
Can everyone hear me? I'm a low talker. The masks are not helping, so just making sure.
There is a microphone there as well, and that's for the room.
Perfect.
Yeah. In the back row, though, I'm going to keep an eye up there. So any in the back row has a hard time hearing, just tell me and I'll adjust the mic accordingly.
Hey everyone, can everyone hear me again? Just checking. Okay, thank you. I'm Smitha Rao, and I use the she and they pronouns. I'm a new faculty member in the College of Social Work, and usually it's me in the department saying, hey, this is what's happening and this is why social workers should care. And this time around, it's a little turned around because you must be wondering what's a social worker doing here. And I just want to talk about my work and also connect it to, just this topic, this very important topic of climate, water, and health. So I work on human and policy dimensions of environmental change, and I focus on environmental and climate justice. This is, like everyone has said, it's such a huge, vast topic, and my esteemed panelists have already given such an amazing background with their perspectives. My training and experience has been as a social worker and a human geographer. And I want to share some of the more social work perspectives on this very complex topic about why this is a moral issue and one of the biggest social justice issues of our time. It cuts across every imaginable space, and it's going to, if it's not already, affecting each and every one of us. On the face of it, these effects of climate change, of environmental degradation should affect everyone. It should be equal. For instance, an extreme weather event such as a hurricane affects everyone in its wake, right? But when you start examining, how the hurricane affects different populations, you start seeing and noticing patterns. You see who's affected more, who's affected continually, who is in a better position, even if marginally, to escape, evacuate, rebuild, to get compensation after, to have a home that might withstand a disaster, or to have insurance to tide them over. So I'm just going to take a few examples to try and tell a story of how equity and justice ties into this broad topic. So research, I'm going to talk about precipitation again a little bit, but research shows that all existing inequalities and climate inequalities and burdens are almost always overlapping. That those who were historically underserved bear the brunt of these events. They often have the lowest resources to cope with and almost always have the most constraints politically and civil rights wise. They also live in some of the most polluted places. And the most severe harms of climate change always fall disproportionately on these underserved communities who are least able to prepare for and recover from these events. So we know that climate disasters are more intense, more frequent as a result of climate change. There's no debate on that. And since we're talking about climate, water, and health, let's focus only on disasters. Thank you, Aaron, for setting that ground, where water is a key component, right? If you look at disasters in the last 2 decades, about 70% of those disasters have had a component of water. They've been water related, with floods, hurricanes, thunderstorms, extreme rains, etc. This picture on your left is from September and October, end of September, early October. It's Cyclone Gulab that hit coastal Andhra Pradesh, which is the east coast of India, and Orissa. Interestingly, it began as a tropical storm in the Western Pacific Ocean, moved across the China Sea, across Thailand and Myanmar into the Bay of Bengal, hit India as Cyclone Gulab. Thankfully, did not become a super cyclone, but was still devastating enough, mostly to farmers because of the time it hit, because crops were ready for harvest and it was standing crops that were affected. And then moved across India, the west coast of India, lost some momentum, and then suddenly strengthened again over the Arabian Sea and transformed into Cyclone Shaheen, which you see on the right, which hit Oman and Iran. Oman, you might have read this, that it received 5 years worth of rain in a couple days. So you can imagine that no government, no system can be prepared for this, right? And such kind of events, that this was a storm that sort of changed its pace almost 3 times, affecting multiple communities, multiple countries as it went. And a lot of the times when it happens in the global south, you don't always hear it because you feel like it's happening every day. It doesn't even make the news sometimes over here. And here in the US as well, we saw in the previous presentation that heavy precipitation events have increased over time and are projected to increase. Episodes of heavy downpour and cloudbursts and rapidly intensifying hurricanes. How many times have we seen that in the last couple of years? The hurricane has rapidly intensified. That drop a ton of rain on smaller geographies have increased multiple times around the world and in the US. A month or 2 ago, we saw the images, the scary images from Germany. Last month, we saw images from New York, the subways flooding, and how we saw the same example of these intersecting disasters, how Hurricane Ida was having an effect all the way across in the northeast of the US. And there too, why I want to bring those together is that we saw that the differential impacts about who was able to evacuate, who was able to survive, who perished, and who continues to suffer, you see the same patterns emerge again. And those impacts don't really appear out of the blue. That's what is most important to note, because these impacts are actually building on historic inequalities, historic legacies of inequalities, of poor planning that favored some communities, that favored some countries over others. That's the fundamental injustice when we talk about climate injustice, that those who had the least to do with it, with what caused climate change, are the ones that are facing the worst of it. So we spoke about too much precipitation. Let's also talk about too little precipitation. That sometimes is called slow disasters, because you don't see them, like they're not sudden onset disasters. So you've spoken about the droughts. There's a mega drought in the southwest of the country. Oh, okay. So the mega drought is because it's lasting for decades, right? In the southwest, across the states of California, Colorado, New Mexico, Arizona, Nevada, I think, and Utah, that drought has lasted about 2 decades now. And this we already spoke about the increase in wildfires that can irritate respiratory systems, right? Who already has worse conditions of asthma in the country? It is communities of color. Why? Because toxic pollutant industries were mostly, race and income is some of the most important aspects of why toxic polluting industries are located, how toxic polluting industries are located in the country. And there are all of these billion-dollar disasters and others, but beyond the economic damage, we're talking about loss of life, of livelihoods, of health, and so much more. It's drought, for instance, is related to compromised quality of drinking water, diminished living conditions. There are health effects, economic and job impacts, compromised food and nutrition, increased incidence of illness, as we just saw. Entire food systems are at risk. Workers and farmers who depend on these systems, people who depend on the system for survival are at risk as well. And adjacent to too little precipitation is the rise in extreme heat events. 2020 was one of the hottest years, and July of 2021 was the hottest month on record since records started being kept the world over, right? And every time these extreme heat events have happened since the Chicago big heat event in the 2000s, while it affects everyone, it makes sense to again examine how other results differentiate, right? Some of the same groups show up repeatedly: older adults, infants, young children, minoritized communities, those without access to cooling facilities, certain occupations that need to be outside just because their occupation demands it, persons who are struggling with housing. So the questions to ask are, who is able to access cooling centers? Whose house is built in a way that probably is prone to overheating? Who has access to green spaces with shade, with water? And if you take it to the global level, a lot of the studies here show that to beat heat, you need to access AC. Think about the global south and how many people have access to the air conditioner and what the massive use of air conditioner is doing to the whole climate sort of cycle anyway. So there are things to be thinking about in terms of equity, and I don't know why this is not showing up. Yeah, consider existing vulnerabilities when you're thinking about extreme heat. So when it's very hot, it's also general advice. If you see the CDC website, will say stay hydrated when you're able to do so. Let's see who's able to do that. In many parts of the world, access to clean drinking water is a daily struggle. And we've seen how the quality of the water is compromised through these different systems at play. So again, a huge inequity right there. And all of these disasters, whether they're the sudden onset ones or the slower disasters, they all have physical health consequences, but there are also multiple mental health consequences. There has been a lot of evidence to suggest that symptoms and reactions such as cognitive dysfunction, anxiety, climate anxiety, for instance, stress and other behavioral reactions, disasters can lead to social isolation, loss of social networks for people, as well as an increased dependency on alcohol, tobacco, drugs, and prescription use for coping. So there is, if you thought that was complicated, there is a whole lot of complication when we add humans to the mix. And one thing to remember is that the effects of climate on human society and our ability to mitigate and manage them and adapt to them are often influenced by social factors. So I want to throw in gender into the mix. Studies show that there is a linkage between climate change impacts and specifically gendered outcomes. For example, more women die in disasters compared to men, or are left behind because of restricted mobility a lot of times. Belonging to historically disadvantaged groups can only increase those risks and those impacts. And also to note that there are impacts of gender-based violence and intimate partner violence rates that go up in the aftermath of a disaster. There is some studies that show that climate change might be linked to climate change and resultant disasters, all natural disasters, but because of climate change, I'm linking them to, are related to early marriage among many communities. And that has its own set of sort of lifetime of outcomes and impacts, that health impacts and physical and mental health impacts. And there are other, like speaking of direct and indirect effects, if you look at, climate change means increase in ocean temperatures, which leads to the loss of coral reefs. Shouldn't be gendered, but when you think about its impact on the tourism industry, and then when you see that about 50% of the tourism industry comprises of women, you will see that it is a gendered impact. It's an indirect impact probably, but there is a direct impact of the oceans warming, the corals, the tourism, and the women. In low and middle income countries, I'm from India, a lot of the rural areas, people often depend on the natural resources for their daily lives and survival, right? And when you talk to them about climate change, the language is different. They don't talk about the language of charts and models and temperatures. It looks and feels different. When you ask a woman in the Himalayas how things have changed, she might say that the distance she has to cover to get water has increased over time. That's the way she is feeling climate change. And that's because the spring near her house has kind of dried up. So a lot of folks also have typically, especially women in many lower and middle income countries, even here really, have lower access to resources and the decision making, leaving them restricted from sort of leaving their communities. One adaptation to many climate impacts is migration. A lot of times in these countries, men migrate. And because women have to deal with their gendered roles, they are staying back, fulfilling their sort of reproductive capacities and taking care of the children and the family and the land. So remaining at home leaves them vulnerable again, because one, this is where climate change is hitting the hardest. And two, it continues to perpetuate that cycle where they're missing out on the opportunities that maybe migrating would have afforded them. And the mental health toll of the stress and the lack of power, nobody even talks about that. So that's another huge thing that we need to talk about. And gender, there's a misconception that it's only about women. It's not. Across all the countries, there is evidence that drought can disproportionately increase suicide rates among male farmers. So gender is an important sort of lens to look at equity and climate impacts from. And I think in 2018, there was a statistic that showed that there are about 38 million people who live in poverty, and about 21 million people were women. And they're more exposed to environmental toxins, more prone to stress, to environmental health, environment-related illnesses everywhere, including the US. And women's participation in climate action plans also remains rooted in existing social norms. And that's where sort of community organizers and building power in the community becomes very important. I will jump to the last. I want to end with the fact that what we have seen again and again and again through these examples is that social forces that operate in our society are key to understand and keep in mind. The existing inequalities need to be addressed as we are talking about climate change. If we don't, we're just going to probably exacerbate them, or it's always going to be a little more challenging if we don't already look at it as an equity and justice issue. For example, I think if you bring a new technology without increasing, sort of having a parallel empowerment program in a community, chances are you're just going to re-entrench existing sort of hierarchies and power differentials. So I'm just going to stop there abruptly.